Okay, hello everybody. Thanks for coming to this hangout for the office hour for the compiler course. I think this week Professor is still on travel, so he cannot join us today. And hopefully everybody have a good long weekend for the last week, and the everything goes well, especially for the project too. Things like we are approaching the end of the semester, so it could be very busy for the next few, maybe 2 weeks, 2 or 3 weeks. So I have set up the proctor track for everybody, and it seems like we have three students are taking the online course for the first time, and actually this is their first time to take the exam, so the on pro track. So I have created a fake, just a test exam, and if you log into your account, protocol tracker account, you should see an example exam. Actually, it's just empty, including just one question. And I suppose like you can log in it with your GTID account if you forgot your password or do not know the password. You can just reset it, but still with your GTID account. So hopefully everything is fine. It's for the project one, for the grading of the project one, it is having delayed because of my personal travel, but I will finish it this weekend, but no later than next Monday or Tuesday. So I'm sorry about that. And actually, for the next office hour, it is moved to 22nd. I think it's 22nd. Yes. So yeah, I think that could be the last office hour. So if you have some questions regarding the exam or regarding the course, you should try your best to attend the office hour, and I can talk to a professor face to face. Yeah, that is all. So Adam, do you have something to say?
The only thing is that I'm planning to start grading homework 3 either tonight or tomorrow night, and I expect it to be done by Tuesday or Wednesday.
Great. Yeah, so project 2 is important, and especially we're approaching to the end of the semester. So it could be very busy. And the major thing is we cannot give you the deadline extensions because we need to finish everything, every grading before a deadline imposed by the institute. So try your best. Seems like we have a quiet office hour this time. Okay, so I'm going to mute myself for a while.
Okay, me too.
Oh, okay. Somebody is asking about the Java starter code and how to use it. Actually, it is just a template help you to like passing the IR code into a more like into a data structure could be useful when you do the block analysis or the IR generation stuff. You're not like in post. You don't have to use it, but if you think it's not very useful, actually, it's just to do some translations, the Python stuff, simply Python stuff, like instruction, and you can do like you can construct it into a data structure represent an instruction, like what is the opcode of the instruction, what is the operand of the instruction, and also you could it help you to identify the blocks. But I haven't finished. I don't think I finished it completely because it is supposed that you can identify what is the basic block, what is the based on the CFG rules. So it is nothing new. But actually, this is our first time to provide this template or static code for you guys because it is the summer. We try to like reduce some workload for yourself because when you do like IR analysis, you do the register allocation or the code generation for the MIPS. You need to pass in the IR code into your memory and then do the dependency analysis, something like that. So this is only supposed to like reduce your code. But so if you don't like it, you don't need to have to use it. Is it clear? For part one, let me go to the description.
So for part one, the IR modification, I think it's really there just to help with the register allocation analysis phase. The easiest example I can think of is um, an IR statement that say was generated from project one from the Tiger compiler might have some kind of um, expression that results in adding two numbers, and you're setting a variable to the result of adding those two numbers, which involves some kind of intermediate variable. So by modifying the IR for part one, this gives you a chance to actually go through and analyze the IR that's input to your register allocator, and physically choose registers that can be used for each of these sub expressions, each of these variables, etc. Because you have to remember that MIPS only has a very small fixed number of registers available. So every operation is going to have to include at least one of those registers. I think if you skipped that part and tried to just go straight from IR to allocated MIPS instructions, it would just be very complicated.
Oh, okay.
At least that's from what I understand of this question. For part one delivery, why do we need to modify IR first? I assume that's what is meant by that question.
Yes, I think we provided some example IR for you guys, right?
I don't know, do we have a start to finish example? That factorial IR program, do we actually have the MIPS instructions as well?
I'm not sure. Yeah, we have, but it's based on the older IR. I don't should be fine. Maybe you have a double check. No. I don't have it. I don't do have some example from your project. Hey, Adam,
Yes.
do you have an example from your test?
I could. I mean, I could produce one using my project.
Oh, okay, that's a good idea.
I don't know how much variability. Like my only, it's. I think it's safe to say that these, like if I provide um, MIPS instructions based on my project, it's possible that it could be slightly different from everyone else's, yet still correct. Would you say that's
Uh,
true?
Actually, don't worry worry about it because there is no like a translation could be like exactly the same thing.
Right.
Especially when you do the code generation.
Right. Yeah.
So
So I just want to make sure that if we publish this, that the students understand that this is not a concrete black and white right or wrong example. This is just one implementation.
yeah, it just yes, you're right. It's just implementation. Actually, just make sure the program itself it is correct. That is good enough. You can like have different structures, but just to make sure the execution is the final execution is correct. I mean, the final
Mhm.
output when you execute the program.
Do you have the Qt SPIM emulator or any of the MIPS emulators working currently?
I think that is from the official website, just the one from the official. They haven't
Okay.
updated it for years.
Okay. I might, because I had trouble getting those emulators to work when I was doing the project. So if you have a version that's working right now, let me send this to you first, and you can double check that the result is correct.
Actually, I don't.
Oh, you
Actually,
don't? Okay.
oh, yeah, I haven't been working on it for years.
Tell you what. Let me see if I can get the emulator working and just make sure that these examples are correct before I send them out, and then I'll post it on Piazza.
Yeah, thank you very much. Generally, it is correct, but actually, the main focus is like you need to focus on two different register allocators. One is naive, another one is based on what we got it based on the basic block, the global basic block. So for the naive one, it is very simple. When you emit an instruction, you just need to like assuming every data is in the memory, so you need to load the data from the memory, do the computation, and storing the data back to the memory. That's it. And for the global register allocator, you need to do some optimizations based on the liveness information. So that means you need to do to do some manipulations or analysis based on the IR, like liveness analysis, to check the love range for each values corresponding to an instruction. And then you decide how the registers in the MIPS can be used to store which one. So it means that you don't have to assume every value is stored in the memory. It can be just start reciting the register. So that is why there is like a static code, like passing the IR into the just read the IR into the memory and represent them into with different data structure like instruction, basic block, or function, something like that. I think that is try to help you to do something about liveness analysis across the instructions and the love ranges. So you need to manipulate into each instructions and their relationships inside, especially how the definition and use chain, something like that. I think all of this could be decided. I mean, when you do the liveness analysis or the definition and use chains, you need something for easier to manipulating when the IR is in the memory. So after you do the code register allocation, something like that, you need to emit the MIPS assembly code. So this is the second part, which we call the code generation. We're taking the MIPS assembly as the target code, and you need to execute it successfully with the MIPS emulator. We're using SPIM. So yes, generally you are correct. So passing the IR is not the major focus here. Passing the IR is just want to help you to do the register allocation, especially for the global register allocation. It seems like maybe we need, but not that much, especially when there is no one-to-one translations. I mean, one-to-one translation about from the IR code to the MIPS code. You need to do the tiling. If there is one-to-one, I think I can just using the simple, like one-to-one, do the one-to-one translation for that. For example, if like the MIPS instruction has addition operation, which exactly the same thing to the addition operation in the IR, working on two registers. you can definitely use that one. But if you say like for the I think for example for the x86, if it can support the addition operation can support the memory access. I mean, taking one operand of the addition operation from the memory, you can do the tiling to handle that case. But you suppose that you just only need to do the one-to-one translations if the instruction is available. You don't have to do the tiling.
Yeah, one thing to add about that, the tiling and instruction selection optimization stuff is really about minimizing individual instruction cost. And I think that's a bit out of scope for this course. What this project is really trying to do, as I understand it, is minimize load stores back and forth to memory. And you can minimize that by reusing as many registers as possible. Because remember, the registers are right outside of the CPU itself. So as many times as you can avoid moving bits from main memory to register and register to main memory, the faster your program will run and the fewer instructions you'll actually wind up with. And so like when we did our project, that the instruction count was actually our first metric. The naive implementation should produce quite a few more lines of MIPS instructions than the globally allocated version. But yeah, we didn't do any tiling or anything like that. It's we built the control flow graph, basic blocks, identified leaders, performed liveness analysis, did graph coloring, all so we could try to pick registers, kind of pre-select registers for certain variables in the program.
Yeah, and that is the focus on the register. The focus is on the register allocation. So you don't have to do tiling. Actually, the purpose of tiling is try to select some quicker instructions, like make the program executing faster by removing some redundancies. I just feel like the tiling is more important in the x86 architecture maybe, because for the MIPS code, for the MIPS instructions following the RISC encoding, it seems like most of the instructions has like very clean design. It doesn't either working on the memory or either working on the register. So there is no much combinations, but I don't know.
Okay, question about algorithms for register allocation. The biggest one is the one that's discussed in lecture. I'm going to try to find the actual video where we talk about graph coloring. The whole reason we're doing graph coloring is because we're trying to find variables that interfere with each other. Still trying to log in. Hang on. Okay, for some reason I can't log in to Georgia Tech at the moment. That really is the algorithm, at least as this project is concerned. The idea is if you can figure out which variables are going to be used the most frequently in your program, that gives you a really good idea of where you should maybe pre-allocate certain registers. So you're going to reach a point if your program has a sufficiently large number of variables at work, you're going to reach a point where you just physically don't have enough registers to handle um, all of the variables that you need to. So you're going to have to load and store. Here we go, finally. You're going to have to load and store. So the trick is load and store as infrequently as possible. So that's what the graph coloring algorithm is all about. You're building this web of variables and you're trying to figure out which ones interfere with the other ones. And let's see if I think about this correctly. The ones that interfere the most are the ones that are going to be problematic. Okay, here we go. It's not, let's see, it's not in the liveness analysis.
Actually, we cannot provide any pseudocode for it. I suppose like the lectures has covered almost everything you need. Actually, for the naive algorithm, there is no much worry about it. Just do load on each value, do something like that. And I think the major point for the Briggs algorithm is do the liveness analysis and the love ranges. Get the love ranges for each instruction or each value, and do the like graph color stuff. And then you will find some of the inferences. Especially at the beginning, you can assume like for each value, you can assign a register to it until there is no like three registers in the architecture, and then you need to decide like which register should be spelled out. I think the general rule here is like you cannot assign the two inferences register, values into the same register. You try to like split them into two different registers. And if you want to minimize the load and store, actually, you need to, what is that to do? especially you need to allocate the most inferences part in a dedicated register. You just avoid to make it inference to others, right? I think MIPS has 16 from I0 to I16, but many of them, especially for I0, it is dedicated to value 0. So there is maybe just a 10 something. For the general registers, I think there are some registers for floating point, some registers for stack frames, something like they are specified.
Yeah, I'm trying to find it right now too. I can't remember where or which documentation we use, but I'm going to see what our limitation was.
I found this documentation. This number is important. Yes, especially if the program heavily utilize lots of that. Actually, even like for simple loop, it could access like multiple. Maybe not.
And yes, that number is very important. That's one of the reasons that the IR provides the int and the float list at the top, because that lets you know, if I have, what is this? It says 32 registers, 32-bit registers for use by integer and logic instructions. I'm looking at the link that Chow just posted. Has a separate register file for floating point instructions, which contains another 32-bit registers called F0 through F31. So if you have 32 registers, 32 float registers, which that seems high. I didn't think we had that many.
Yeah, it seems high. I remember some 16, but maybe they have updated it.
Yeah, maybe it's because it's 32-bit float registers, and typically when we think about floats, we think 64. Because I remember thinking we only had 16. So maybe we were assuming a 64-bit float register.
Especially actually just in terms of like 32 general registers, the integer registers, some of them are reserved for some special purpose, like
right.
Register 0 is just a 0, so you cannot write data to it. You're just reading data from it, which is exactly 0. And also there is some registers especially reserved for storing some like stack point, frame point, and a return address, something like that. So when you do the computations, actually the only registers you can use is some like temporary registers for temporary data. Yeah, so you have to read the document, the MIPS document, architecture document, to make sure which registers you can use. Like, you can put in, like when you do generate the code for a function, you have some epicode. That means you need, at the beginning of the function, you need to save some values of registers using push or pop operations like to the stack, and you need to manipulate some like stack point or based or the stack base point values, something like that. Even the return address of the function. So you need to reserve some values, and when at the end of the function, you have to restore these values to the. I mean, reserve is like you need to push the value from the register to the stack, to the memory, and you need to restore it from the memory to the register at the end of the function. So that means you cannot using the frame point or stack point or so during the for your code generation. So
yeah, in our version, we set aside 10 general registers for T0 through T9 and 14 float registers, or F0 through F26. But remember, that's where I was talking about we were using 64-bit integers instead of 32. I mean 64-bit floats. So one of the tricks is after you've done liveness analysis, you know how many variables your program needs to work with, and you can compare that to how many registers you have available. You should make sure that when you're pre-allocating registers, if you go that route, you need to keep some free just so that you have spill space. So in other words, the most number of registers that a specific instruction might involve is 3, I think. So if you're pre-allocating registers for your functions as a whole based on graph coloring and such, you want to make sure you leave 3 so that you can handle any kind of spill from any other instruction. Or at least that made sense when we were doing ours. There might be a more sophisticated way to handle that, but we didn't get that far.
Well, actually, if you find like after the graph coloring, you find that the minimum number of registers is smaller than the general register. I mean, the variable registers. Yeah, I think it's in this case it is very easy to do the code generation because you can using just like simply using every register for each value, just using a register for that, right? I think the complex case, you need to do this spurious stuff in the complex case is that like the minimum number of registers after the coloring is larger than available, I mean, architecture registers. In that case, you have to do spur in the code. Okay, so we are approaching to the end of the out of time this time. So good luck to everybody for the final few weeks and for the project too. Actually, I think it's also a good time to start preparation for the final exam. And for the preparation of the final exam, I think the most important thing is homework, as well as the project. I mean, based on the project, I think you should have some basic understanding of the concepts and how they works. And based on the homework, you should get some like experience how to like apply these contexts as well as the project. So the most important thing is the questions on the homeworks. Actually, they are very critical to the final exam because they covered almost every important topics in the exam. I mean, in the course. So good luck to everybody. So see you next time. And for the next office hour, it is moved to 22nd. So instead of next Friday, I mean 22nd should be Thursday, Tuesday. 10 days, yeah. So see you.
All right, see you.